My name is Sean McCartney, and on behalf of my colleagues from the ARSET program, I'd like to welcome you to the third part of the ARSET training on Earth observations for disaster risk assessment and resilience. Today's webinar will be focusing on disaster risk assessment case studies using remote sensing data and open source tools. We are excited to have guest speakers from the New York State Department of Health and the World Resources Institute as they describe how remote sensing data is being used for applications such as enhancing extreme heat surveillance, open source tools created to identify and evaluate global water risk, and an open source platform used to host global datasets with examples on how the Resource Watch platform can be used to mitigate disaster risk. Our first presenter is Dr. Tabassum Insaf from the New York State Department of Health. She will be presenting on how New York State utilizes satellite data for extreme heat surveillance efforts.
Hello, everyone, and thanks for taking the time to learn about our efforts to use satellite data to enhance extreme heat surveillance in New York State. My name is Tabassum Insaf, and I am the Research Director at the Bureau of Environmental and Occupational Epidemiology, and I lead the project that we will discuss today. So this will be the outline for our presentation today. I'll discuss how satellite data provides us with an enhanced exposure assessment of climate change and how we've used this information in New York State to inform health research that helps inform some public policy. And then finally, we'll discuss our outreach and communication efforts that we've used for different audiences. So the reason we looked into satellite data for our program was because we had been limited to using monitor data in the past. And if you can see my pointer, the first picture here is the state of New York. And it's a large state with varying geographical and demographic characteristics. Downstate New York here, where New York City is, it's a metropolitan region, obviously, and it has a surrounding coastline, while upstate New York has the Adirondack Mountains in the east here and the Buffalo and the surrounding Great Lakes in the west. So as you can see in the first map, this shows county boundaries over New York State. So the gray lines are the county boundaries, along with the monitoring stations. So all those dots are different kinds of monitoring stations across New York. And there are multiple counties here in New York where there are actually no monitoring stations. And the rural areas are especially underrepresented. So we did not have information in these areas before. The second map here is a simple spatial interpolation of these data. So we use 30 different monitors that had at least 60 years of data to estimate climate trends. And we can see that there are regional differences in how climate has changed across New York State, but the spatial interpolation is very crude. So you can see here we're borrowing from stations that are very far apart. So we were funded by NASA ROSE's program. We applied for it, and we were funded in 2015. And this has allowed us to use the 12-kilometer national North American land data simulation system that is available for the contiguous United States. And this allows us to capture spatial variation within counties. We further downscaled this data to a 1-kilometer grid, and this is the last map here at the bottom, the downscaling was done using MODIS land surface temperatures, and this I'll provide further details on. So you can see that there is a vast difference in where we were before as compared to the information that we're gleaning from the satellite data. All right. So why should we care about extreme heat in a temperate region like New York State? So you can see the map on the right. Summer temperatures across New York have been increasing. This map displays temperature anomalies by census tract. So the temperature anomalies are basically differences from the norm. And the norm for each census tract was based on a 30-year average temperature for that specific census tract. So although we do not have frequent heat waves or extreme absolute temperatures in all areas of the state, as compared to the average temperature for that area, the temperatures show a warming trend. So you can see as we go to the more recent years, the map looks hotter or redder. Um, the annual average temperatures have been increased by over 2 degrees Fahrenheit since 1970 for almost all of these areas. Over the next century, average summertime temperature in New York State are projected to increase between 3.6 to 10.8 degree Fahrenheit for different counties based on specific energy scenarios. So just a little bit of description about the data set that we've used. The National Land Data Simulation System is meteorological reanalysis, providing hourly air temperatures and other variables on a 1/8 degree, 12-kilometer CONUS grid for 1979 to the present. It's actually, in fact, of a little bit more coarser resolution because it's interpolated from the 32-kilometer North American regional reanalysis. So at this resolution, although we do have a uniform spatial surface, small-scale features like the urban heat island or near coastal temperature gradients are not captured. So what we did, or actually our collaborators at the University Space Research Association, used this technique where they took 8-day composite means from the MODIS LSD, and they captured the spatial patterns of temperature within each larger 12-kilometer grid cell. So the MODIS LSD is either 1 kilometer. We took an 8-day composite of that 1 kilometer data set and used that to look at spatial patterns within a larger 12-kilometer grid. And these standardized departures here were then applied to the air temperatures uh, in this equation to calculate our air temperature at a 1 kilometer scale. More details of these are available in our previous webinar that was done in 2017. So this map is of the New York City region. So this is the New York City, larger New York City region, downstate New York, and you can see that we would expect that the urban areas experience greater temperature variations due to the heat trapping effects of impervious surfaces, known as the urban heat island effect. Now you can see on the right that the 1 kilometer data set allows us to capture some of these variations as compared to the 12 kilometer where it's all uniform. So we believe that the 1 kilometer data set is helpful when you are looking at these small scale variations. So we went ahead and we performed validation of this 1 kilometer downscale data set using New York City's community air survey monitors. And at the bottom of the screen here is our manuscript that was just published on this validation if you would like to know more. And as you can see, the model performs well with R squares ranging from 0.83 to 0.95. So here, the downscale 1 kilometer are the smaller squares here. This is a 12-kilometer grid, and you can see we had about 115 New York City ground stations within this area at different points in time. So the validation was performed using these monitors. All right. Um, So similarly, we have worked with the Florida Department of Health and Florida State University to conduct similar analysis across that state. And so both we were in collaboration with Florida for this project. And these maps show the 12-kilometer NLDAS and the 1 kilometer downscale data set capturing the variations in the coastal city of Tampa and the surrounding region. So you can see that there is a variation in the coastal line here, which is not apparent in the 12-kilometer data set. And we conducted a similar validation in Florida. And if you look at these charts, the red lines are the monitor data, the green are the NLDAS 12 kilometer, and the blue are the 1 kilometer downscale data set. And these estimates, so just to orient you to the charts, this is for all summer months, and these are monthly charts. And we are looking at 10 different um, indicators for temperature, which, the descriptions are here. The top indicators are based on days of the month, and the bottom indicators are based on absolute degree centigrade measures. So you can see that there is actually a pretty good match for most of these indicators, especially for the measures that are based on the means of maximum or minimum temperature. So we don't really, I mean, we do quite a good job, but for capturing days per month above an threshold. But when you look at the means, there is a near perfect match here. All right. So the next section will highlight how we've used these data in research that has then led to enhancements of public policy. So we used spatial or geographic linkage of health data sets to these air temperature data, and we also linked some census sociodemographic data. And for more details, again, this was discussed in detail in our previous ARSET presentation, and I'm going to be presenting the results here. Um, so after using a Crace crossover method, that was the epidemiological analysis that we used, uh, we found that a 5-degree change in heat index increases the risk of heat-related illness by 70%. So 1.69 is the relative risk here. So just to orient the folks to you to these charts, each point here represents the relative risk for a 5-degree change in heat index, and the bars are the 95% confidence interval around that estimate. Any estimate where the lower confidence interval is above the reference line of 1 denotes a statistically significant risk. So we looked at risk due to heat exposures up to 7 days before the illness. So the first estimate, lag 0, is risk on the same day of illness, and lag 1 is risk due to exposure a previous day or day 1 day prior to the day of illness, and so on. So these results suggest that the risk of illness remains significant 5 to 6 days after heat exposure. And so the first chart is for risks due to for heat stress, and the second chart is the risk for dehydration. And we also looked at renal illness and cardiovascular illness. Similarly, these charts show a comparison of risk between rural and urban areas. So as I had mentioned earlier, urban areas are expected to trap more heat due to an abundance of impervious surfaces and lack of green space that can lead to an urban heat island effect. But rural New York is actually also unique because these areas are mostly lower income with abundance of older housing that lack air conditioning. There are also a lot of farming and outdoor activities during the summer, and people may perceive themselves at the lower risk due to an overall temperate climate. So we were, therefore, uh, we were trying to look at, how the risk in rural areas differs from urban areas. And contrary to what would be expected for other rural areas, we find that individuals in New York State are at as high a risk for heat-related illness as in urban areas. So you can see that these estimates are pretty close together. This is um, risk for New York City, this is the risk for rural New York State, and these are for the risk for the rest of the urban areas. And those estimates are pretty close together, although the confidence intervals are wide because there were a lower number of cases. But this just means that when extreme heat does occur in rural New York, people are very sensitive to the health effects. So just to present here an overview of the warning and advisory criteria that was used prior to our research. The regional National Weather Service forecast offices issue excessive heat alerts, advisories, watches, and warnings based on a maximum heat index forecast over 24 to 72 hours. Now, previous temperature thresholds for heat advisories and warnings in upstate New York were established over 20 years ago, and these were not based on local heat health associations. The NLDAS reanalysis dataset provided us the opportunity to conduct these heat health analysis for all regions of New York State, and we reassessed the criteria for heat advisories so that they were now more relevant to temperature experience in New York State during the summer. So this is our previous advisory criteria. Um, and you can see that the heat warnings were being issued at 100 to 104 degree Fahrenheit. So that's pretty high for this region. Now, then we decided to look at the thresholds for risk of illness. So these charts here show the risk of illness at different values of maximum heat index. The excess risk temperature, the red dots on these charts, were defined as the lowest temperature at which the lower bound of the 95% confidence intervals of the relative risk for a particular health outcome was greater than 1. So this is where we start seeing statistically significant risk, and you can see that there is a sharp increase up here. So for heat stress, we find that the excess risk temperature is 83.4, while for the other illnesses, they are for between 75.2 to 78.2. But you can see if you look here at 95, that's where there is a steep increase in risk for these illnesses. So at the pre-existing National Weather Service threshold of 100 degree Fahrenheit, you can see if you look at this chart here, there is a pretty significant amount of risk. The risk ratio for heat stress was 3.727, while the risk ratio for other health outcomes range from 1.72 for dehydration, 1.53 for acute kidney failure, and 1.41 for CVD, or for cardiovascular disease. In contrast, if we were to reduce the warning at 95 degree Fahrenheit, the risk ratio for heat stress is 1.927. And again, and a little bit lower for the other illnesses. So if we were to move the warnings to a conservative threshold of 95 degree Fahrenheit, we would reduce the risk of illness pretty significantly from that would be experienced at 100 degree Fahrenheit. So based on these, we decided to advise a threshold for 95 degree Fahrenheit. Um, Recognizing that the excessive heat warning or heat advisory criteria should be based on regional climate variability, and that the effect of excessive heat on the local population, the National Weather Service actually encourages all their regional offices to work with health departments and develop criteria that are based on the scientific evidence derived from local data. And we were able to provide this evidence in the form of the charts that I presented before you. And so we recommended that this be revised. And so this is our new advisory criteria where it has been moved for the region to 95 degree Fahrenheit. So this, we believe, would capture a high proportion of heat events likely to result in significant morbidity, while avoiding the warning fatigue if frequent advisories were issued at lower temperatures. So based on the findings, we actually were able to revise the criteria for 4 local National Weather Service offices, actually the region of New York State and surrounding Vermont. And this was effective June 1st, 2018. So that's one policy, and then I will also kind of touch on some of those policy implications in our outreach and communication section. So our effort was to develop some different communication avenues for different audiences that would be interested in this research and its findings, including the general public. So since we're a state public health department, it is important for us to translate our findings into easily understandable information that can be used by lay people to protect their own health, and for the community or local health departments to use it to inform their public health actions. And this slide shows some infographics that were developed from this project, and these are all available for download from our website, and we also make it available to the local health departments. So this is just a simple summary of what we found, some engaging graphics, and then a list of resources for mitigation. We've also developed county heat and health profiles. So for each county in New York State, people can look up their heat exposure profile, heat-related health outcomes. So we have some exposure metrics. We have heat-related health outcomes that kind of provide the burden of heat-related illness in their specific counties. And then we have some resources that can help with heat mitigation. So for example, you can see this is a temperature trend chart for Cortland County. So here in this chart, the baseline is the 30-year average for that specific county. So here it happens to be 73 degree Fahrenheit. And this 30-year average was calculated from 1980 to 2010. And the blue lines represent any annual temperatures that were lower than that 30-year average, and the red lines represent annual temperatures higher than the average. And you can see that since 2011, most years have been about 1 to 2 degrees higher uh, than um, than the norm for that county, and 2016 being about 4 degrees higher. And this pattern is actually repeated across most counties in our state. And on the right, we present some burden of heat-related illness in the county for the same for the past 8 to 10 years. So another avenue of dissemination of information is our environmental public health tracking portal. New York's environmental public health tracking program focuses on tracking environmental health patterns and trends. It is a national program that is led by Centers for Disease Control and Prevention, and we are funded to develop this public portal, which improves access to environmental health information and supports research programs and policies that may help protect our communities. So that includes some heat-related data. And we are currently developing or enhancing this portal to generate some data displays that will allow people to generate the figures and download the associated data on demand. So currently our portal only displays county level data. However, we've been funded by CDC to continue development of a sub-county portal that will allow us to provide our local health departments with tools that they can use for their own assessment of climate effects on their jurisdictions. So for example, this chart shows daily maximum, minimum, and average temperatures and the maximum heat index for one county in 1 year and month. And then there are drop-down menus that you could use to choose some of these indicators. Again, this is a summer anomaly chart that you can generate for your county and for specific years, or and then all of the data associated with these would be available for download as well. Um, Along with that, we look at some sub-county measures, so we can provide some maps where people can look at the areas within the county that experience higher temperatures. For example, this is a county map of Albany, and you can see that these gray lines here are the census tracts, and you can see that the inner city areas of Albany experience higher temperatures. This can help local health departments identify where to set up cooling centers in case of a heat event. All right. Another avenue where we've been able to inform some of our policy or programs using this research has been the New York State Home Energy Assistance Program. And this is a program for low-income residents who may have a demonstrated medical need for cooling device in their home. So these are our eligibility criteria. So what we did for that program is we compared the burden due to heat and cold related illness. And you can see that this is, the rate of illness is pretty similar across New York State for both of these illnesses. But when you look at the amount of funding that was being allocated before, 99% of the budget for the program is going to heating benefits, while only 0.59% was going to the cooling benefits program. What we were able to show was this map, which kind of shows the burden of illness as compared to the amount of allocation. So if you can see that the diagonal from top right to bottom left shows equitable distribution. So the purple areas are where the burden of illness is high and the cooling benefit is high. So it is corresponding to the burden of illness. And the whitish areas are where the burden of illness is low and the cooling benefit distribution is also low. But the problem areas are these areas where the red areas here show is where the burden of illness is actually pretty high, but they have a low cooling benefit. And similarly, for the blue areas, although there isn't much burden of illness, uh, especially here, then but there is a lot of cooling benefit being distributed. So there was some inequity in the distribution, and we were able to show this to the program. The program also was able to provide additional 3.5 million dollars for this program to the cooling budget after analysis of the funding trends and the projected utilization. So the cooling benefit has increased in the past year. Another program that we feed into, and this is the final program that I'll discuss, is our Climate Smart Communities program, which provides incentives and certification to local jurisdictions, counties, cities, or towns that complete some action towards climate mitigation and adaptation planning. This could be taking action to reduce greenhouse gas emissions or do activities to adapt to a changing climate. And the benefits from the program include leadership grants, leadership recognition, free technical assistance, and access to grants. Satellite data can be useful for such efforts, and the subsequent research results can be applied to estimate local climate trends, health benefits of climate change mitigation, and assess local areas of high vulnerability. So that's where we've been able to feed into this program. And this file slide provides an overview of the different avenues we've used for dissemination of project results. Our work has been featured on the NASA website, so that's a public-facing website, and for specialized training in the ARSET webinars. We've also presented at multiple national and international conferences, and we will be presenting at the upcoming annual meeting of the American Public Health Association in Philadelphia if you're attending. We've also tried to present to different audiences that may or may not be familiar. So we've been at the American Geophysical Union and American Meteorological Society, which may not know about public health applications of satellite data. And finally, we have presented to local audiences through our Public Health Live presentation and local meetings of public health professionals. And finally, we've used social media campaigns to spread awareness, especially during hot days, and discuss some of these efforts. So the final slide I have is an application that is under development, and it's called a story map. This is a draft version, and this we are developing so that it's a little more interactive and displays some of this information in a more colorful and easy way. So this would be available. People can scroll through the story map, and you can see some of these charts showing climate trends, the number of heat waves that can be seen increasing across the years. This screen shows you a slider where you can see a snapshot comparing the climate between 1979 to 2016, and you can see there is a dramatic change. Again, these are summer anomalies, and you can click on your county and look at their county heat profile. We have a burden of illness chart. We will be presenting the heat advisories. We link out to the National Weather Service for some more information on their efforts, what to do when there is a heat event and who is most at risk. We have a heat vulnerability index that was developed earlier, which kind of provides an overview of community vulnerability. And here people can type in their address and look at the vulnerability within their county and get some measures on who might be at risk and what might be causing that risk based on these different criteria. And then finally, after identifying these community vulnerabilities, we provide information on some resources like the cooling centers. We have an app which shows where the nearest cooling center is. So that links out to the app where you can put in your address and find the nearest cooling center, information about the cooling assistance program, and also information about our Public Health Live webinars that talk about climate smart communities. So that's an upcoming application that would summarize these in a more user-friendly format. So finally, I'd just like to thank our co-investigators, collaborators, and stakeholders who have made these efforts possible and whose invaluable input has helped make our project a success. We were funded along with the Florida Department of Health and New York City Department of Health, so some of these efforts are mirrored there. And then the University of Alabama Huntsville, University Space Research Association, Florida State University were our academic partners who helped with the research portion. And then our stakeholders, the National Weather Service, New York State Energy Research Development Association, and the New York State Climate Smart Communities Program have helped us develop some of these outreach messaging, and the Environmental Public Health Tracking Program and the BRACE program have been co-funders. So we've used those avenues for dissemination as well. So thank you so much for being a great audience, and I will be happy to take any questions that you have for me at the end.
Thank you, Tabassum. Our presenters in the second half of the webinar are from the World Resources Institute. Corey Filio, Samantha Kuzma, and Amelia Snyder will be presenting on Aqueduct and Resource Watch, open source tools and platforms used for disaster risk management.
Hi everyone, my name is Corey Filio and I am presenting to you guys from the World Resources Institute. I just want to say very quickly thank you to our friends at NASA ARSET for sponsoring this. I think we're really all very excited to present to you these excellent tools. And we're going to be talking about some of these data tools that we've created for disaster management. But first, I wanted to give you a little bit of background about WRI more generally. So WRI's approach to global change is a little bit interesting because we are a global environmental think tank. So we kind of try to think very broadly, we try to tackle large issues, and we try to create more sustainable change so that current and future generations can live a really healthy and successful life. And how do we do that? So our approach is generally to count it, change it, and scale it. So we want to do the kind of research that leads to impactful and replicable change. And we do that globally. And so we have all these different international offices operating around the world. We have programmatic offices as well. And this is just to make sure that our work is really diverse. And that cuts across this thing we call the matrix. And so all of our work is cross-sectional because like the real world issues are cross-sectional, we want to make sure we're looking at solutions that do that as well. And so part of that work that we do is looking at open data. So WRI as an institute has committed to being a driver for open data, not only for our own research, but working with partners and global stakeholders to get their data out of silos and into the hands of people that can use it for positive change. And so one really great example of how we've done that is working with Global Forest Watch. And Global Forest Watch was the first open data platform that WRI created back in, I believe, 2014. And so Global Forest Watch monitors tree cover loss and things related to deforestation. And it's a really powerful tool for monitoring forests. And so here there's a great example in Nigeria of how a local community was able to monitor and protect their land. We also have an excellent example here about the role of oil palm in deforestation. And so a lot of companies end up using things like this. So we have a variety of different audiences for the suite of data platforms that WRI hosts. GFW in particular works quite a bit with companies looking to monitor their forest footprint. Here's a really excellent example. The National Forest Authority rangers were able to look at illegal logging happening using the Forest Watcher apps done through the Global Forest Watch program, and they were able to find the culprits and make sure that that was stopped. And finally, I think one of our favorite examples of this idea of being able to monitor and mobilize using data to create real-world action was when United Cacao, who was a self-proclaimed sustainable company who worked with cacao, we were able to see with GFW that they were not farming where they said they were farming. There was a lot of forest clearing happening, and because of that and because of the announcement we were able to make, there was significant reputational damage and financial damage done to the company, and they ended up stopping that activity. So this is just one example of how we've kind of taken the idea of data into action and turned it into these platforms where you can interact with satellite data, remote sensing data, kind of all in one central place. And so the tools we're going to be talking about today are Aqueduct and Resource Watch. So first up is Aqueduct, and I'm going to pass it over to Sam now, who's going to talk about that.
Hello, my name is Samantha Kuzma. I am a GIS Research Associate with the Water Team at WRI, and I'll be walking you through a demonstration of Aqueduct. Aqueduct is a suite of tools that can be used to identify and evaluate water risks around the world. Our tools map water risks such as flood, droughts, and stress using open source peer-reviewed data. Over the past 6 years, the Aqueduct tools have reached hundreds of thousands of users across the globe and informed decision makers across sectors. 7 days ago, on August 6th, we launched the latest version of Aqueduct, which includes new and improved tools, indicators, and an upgraded underlying hydrological model. But before I show you the new tools, I want to revisit our roots. The current Aqueduct tool is over 8 years in the making. In 2011, WRI launched the Aqueduct Alliance. It's our coalition of companies working on water stewardship, along with the first tool prototype to measure and map water risks. In the years to come, we've updated the tool in a few ways, including releasing the first ever global country rankings of water stress and adding projections of future water stress. We also created something called the Aqueduct Flood Risk Analyzer. Now, 2019's Aqueduct, we've updated the hydrologic model, improved our indicators, and we've expanded our suite of tools. Our new suite of tools includes updated versions of the Water Risk Atlas and Aqueduct Floods. It also includes 2 new tools, Country Rankings and Aqueduct Food. Right now, only the Water Risk Atlas and Country Rankings have launched. Aqueduct Food and Floods will be available this fall. Each of our tools were designed with a specific audience in mind. We recommend choosing your tool based on the information and functionality that you need. So you can use the Water Risk Atlas to map current and future water risks. With this tool, you can analyze exposure to physical, regulatory, and reputational water risks across multiple locations. Plug in your own locations or explore the map yourself. Use Aqueduct Country Rankings to understand national and subnational water risks. With this tool, you can compare and rank countries, states, and provinces by their exposure to water risks. Just a note, this image is a mock-up. You can now check out the just released tool to see the official data. You'll be able to use Aqueduct Food to understand current and future water risks to agriculture and food security. With this tool, you could identify crop exposure to water risk and visualize implications for trade and food security. You'll be able to use Aqueduct Floods to identify where and why flood risks are emerging now and in the future. With this tool, you can identify coastal and riverine flood risks and analyze the costs and benefits for investing in flood protection. So based on these descriptions, I'd say that the Water Risk Atlas and Aqueduct Floods are the most relevant tools if you're interested in exploring disaster risk management. So let's walk through both of these tools and explore how you may use them in your own work. So let's start with the Water Risk Atlas. As I mentioned, you can use this tool to map and explore water risks, both current and in the future. Key research partners for this tool include the University of Utrecht and Deltares. So our framework includes 13 different indicators of water risk. They are designed to show chronic long-term trends in water. Categories include physical risks to water, such as water quantity and water quality, as well as regulatory and reputational. We also aggregated our 13 indicators into an overall water risk score. You can adjust the weighting used in the aggregation based on your own interest. To explore these indicators more, let's jump to Mozambique. Okay. In March of 2019, Mozambique was hit by Cyclone Idai. This storm caused catastrophic damage and over 1,000 people lost their lives. While we can't use this tool to predict such devastation, we can use it to try to examine and understand Mozambique's risk to water-related threats. So let's start by looking at interannual variability. To learn more about any of these indicators, you simply click on the eye icon. For example, here we can read that interannual variability measures the average between-year variability of water supply. Higher values indicate wider variations in available supply from year to year. And here you can see that southern Mozambique actually has extremely high variability in its water supply year to year, while the northern region is a little bit more stable in its supply. You might ask yourself, are there times during the year that you might experience more variability than others? And with this tool, for a subset of our indicators, you can actually now explore how these risks shift month to month. So again, looking at interannual variability, we can see how water supply across January from year to year ranges. So we still see high variability in the south, but we also see that risk is intensifying in the north. So moving to March, which was the time of year when a day hit, we see that most of Mozambique's water supply in March is widely variable. March is a month that experiences higher highs and lower lows compared to January. And we saw this past March how high those peaks can go. But variability can actually be managed. So to better understand what's happening on the ground in Mozambique, let's explore flooding. So I'm going to move back to our annual indicators, and I'm going to move down to riverine flood risk. Riverine flood risk measures the percentage of population expected to be affected by riverine flooding in an average year, accounting for existing flood protection standards. Higher values indicate a greater proportion of the population is expected to be impacted by riverine floods in terms of average annual impact. In Mozambique, we can see a pretty high risk of riverine flooding. Now, if you wanted to zoom in and learn a little bit more, please go to aqueduct.wri.org. You'll be able to click on the map and analyze risks at specific locations. But I think that this is an interesting finding that flood risk is pretty high in Mozambique. So let's move over to our other tool, Aqueduct Floods, so that we could better understand this hazard. So just as a reminder, Aqueduct Floods has not launched as of the recording of this webinar. So all of the tool and the data that we are showing today is considered to be preliminary and should not be used to inform decisions. Aqueduct Floods takes a traditional look at risk. It examines the hazard, exposure, and vulnerability. Our key research partners for this tool are the Free University of Amsterdam, Deltaris, the University of Utrecht, and PBL. So first, let's explore the actual flood hazard. On our flood hazards tab, we can see inundation depths for both riverine and coastal floods. We can see how inundation intensifies with greater flood magnitude. And we can also see how inundation changes through the years, looking into the future. Now, to understand the risk better, you can move over to our risk tab. So this tab calculates flood risk for the years 2010, which is our baseline, 2030, 2050, and 2080. Here you can investigate how flood risk will change through time due to climate change and socioeconomic drivers. As a default, we'll display the results using a business as usual scenario, which is based on the IPCC pathways. But users can also examine optimistic and pessimistic scenarios by clicking on the Show Advanced button. Also within this tool, you can type in the name of any country, state, or river basin. We also have 120 cities that you can explore. You can even compare these with other places. You can evaluate riverine and coastal floods. And we also allow users to choose between 3 different types of exposure: urban damage, affected population, and affected GDP. So looking at the results section, you can see our first graphic is a table that summarizes flood risk. Here you can see the annual expected urban damage, as well as the total asset value for each year. So in Mozambique today, around 2% of all urban assets are expected to be damaged annually by riverine floods. By 2080, we estimate the number will rise to about 5%. We can also see that Mozambique has little to no flood protection to mitigate against these risks. This row actually accounts for how climate change may change flood protection levels through time. There are other great graphics on this tab, but I'm going to move us over to the cost-benefit analyzer. So this tab is going to help you answer the question, well, what can I actually do about floods? The cost-benefit analyzer assesses the feasibility of investing in dike infrastructure to mitigate the impact of flooding. All of the calculations are done in real time, so it does take a bit longer to load. Again, here we allow users to pick a scenario for future projections. We also allow users to customize information for the CBA, the cost-benefit analysis. Those customizations include the current and the future desired flood protection levels. They include the year that the flood protection design should be valid for. For example, you want to be able to protect against 50-year floods in the year 2050, and many more. And always remember to hit apply changes after you have altered this window. So we provide default values for all of the parameters that I just showed you. Two in particular are really interesting. Our estimates for current flood protection come from a model called FlowPros, and this offers state-level estimates of flood protection around the entire world. We also offer country-level estimates of construction costs. Okay, so let's look at our results on the right side of the tool. Our first graph shows us the cumulative net benefits, so taking into account both the cost of construction and maintenance, as well as the benefits from avoided damage. And we can see here that by the year 2040, which is 20 years after we said construction starts, Mozambique would actually start seeing net benefits under this scenario. So our next graph breaks the cost and benefits down even farther. You can see that once construction is done, the only costs that remain are operation and maintenance, whereas the benefits from avoided damage keep accumulating. So just looking at more results, we can see that we estimate that 85 million people will avoid being impacted by floods through this design. And our cost-benefit ratio is well below 1, meaning that this is a pretty feasible investment. Using this tool more, we just offer other graphs that help you understand the calculation underlying these results. So now that we've screened Mozambique for water risks, investigated its flood risk into the future, and assessed the feasibility of investing in its flood protection, now we can jump to another WRI platform, ResourceWatch, so that we could learn even more about the world.
Hi, this is Amelia Snyder, and I work on the data team for ResourceWatch. And ResourceWatch is another one of the World Resources Institute's great open data platforms. And while Aqueduct hosts this new data that they have developed themselves, ResourceWatch actually goes out and collects the best data that's already out there from a wide variety of trusted sources and shares it in a way that's transparent. We host hundreds of reliable and timely data sets that cover the entire planet. And today I'm going to show you how you can use our platform and our data sets to mitigate disaster risk. Just to give you some background, ResourceWatch was created a little over a year ago as a partnership between WRI and 30 global organizations with a shared mission to use open data to change the world. As I'm sure many of you are aware, when you try to find data relevant to your work, there are often hundreds of different options out there for the data that you're looking for. There's been this big push to create new sources of data from satellites or crowdsourcing tools, and some of these data sets are inaccessible because you have to pay for them, or they might be shared without clear methodology, so you don't know if it's trustworthy. So there's tons of data out there that you have to sift through, which really impacts our ability to respond to situations with urgency. ResourceWatch aims to make the process of finding data much simpler by carefully curating the best data from a variety of sectors so that decision makers can focus on using it to create impact. ResourceWatch data covers dozens of global issues at the nexus of sustainable development and the environment. Currently, we're hosting over 260 data sets, over 45 of which are near real time. And while many data sources and platforms are really specialized or siloed into one of these topic areas, ResourceWatch aims to bring them all together so that you can find contextual information or explore the intersections between these different topics. So let's take a look at our platform so you can see exactly what it looks like. So when you land on the ResourceWatch homepage, you'll see that we have our latest stories from our blog. We have some of our topic pages. We have ways that you can explore the data and take a deeper look. And we also have ways that you can get involved or contact us. So let's take a look at one of these topic pages first. We have them on a variety of different topics related to sustainable development. And I'll show you the water page just to give you an example of what these look like. So these topic pages are really meant to give you a great overview of what the current state of this topic is. It has a lot of great images and figures pulled from our data sets on ResourceWatch, as well as maps. And this is a great way just to get an overview of these topics if you're really just trying to get an introduction to the area and you don't know much about it. So this is a great place to get started. You could also take a look at our blog. And our blog is managed by our data journalist, and she works together with our data team to sort of pull some interesting stories out of the data sets on ResourceWatch. So she works together with them to do new analysis and pull out some interesting insights from the data and write these great little pieces that help get you inspired about the data that you're looking at. But the piece of the website that you all might be most interested in is the data. So you can find that on our data tab, and we'll first look at Planet Pulse. Planet Pulse is where we feature all of our near real-time data sets. And you can see we've got near real-time data sets from a variety of different topic areas. You can just scroll through them here. And you can click on any of them to add them to the map. So right now we're seeing where there are current landslide warnings happening in the world. And you can scroll around to see whatever area you're interested in. Or you could add contextual layers like population information to see who might be impacted by this. And this landslide warning data set is updated every 30 minutes, and all the data sets on here are updated in near real time. So this is really meant to give you a good idea of what the current pulse of the planet is. So the main part of the ResourceWatch website is our Explore Data catalog. And you can find this by going up to Data and clicking Explore Datasets. And this is where we house our 260 plus data sets, including those near real-time data sets that you just saw. And you can search through these data sets by filtering them by different data types or frequencies or time periods. And this is also where we host that aqueduct data that you just saw Sam showing you. So we can pull that data up on the map. And this is a great place to come if you want to start to find more contextual information. So we can add some contextual layers like dams and population. And you can add as many layers to the map as you want, and they'll just keep layering up on top of each other. And you can move these layers around to visualize them however you like. You can turn them on and off. You can also change the base map to help the visualizations or add boundaries. And you can change the opacity so that you can more easily see these rasters on top of each other. If you're interested in a particular location, you can use our search feature to zoom right into that area. And once you've made a visualization that you like, you can export it, giving a URL to ResourceWatch or using this embed code to put it right on your website. And one other great feature is all these layers have a little layer info button that tells you exactly what you're looking at and has a link to the full metadata page if you click on the More Info button that tells you more about the data set. Okay, now we're going to take a look at an example of how you could use ResourceWatch to look at disaster preparedness using some contextual data. We're going to do this by comparing what happened in Hurricane Harvey with Cyclone Idai. So first I want to just show you some quick numbers to compare these two events. You'll see that Hurricane Harvey was a larger hurricane. It had a higher cost in damage, but many fewer fatalities. So Cyclone Idai was a lower category storm, but it had many more fatalities, and Hurricane Harvey had significantly more damage to infrastructure. So we can use some of the contextual data on ResourceWatch to understand why each place was affected in the way that it was. So what we're going to do is a side-by-side comparison of the factors that contributed to these impacts between Mozambique and the surrounding area and Texas. So first, let's take a look at GDP. GDP is a good indicator telling you how well an area's economy is doing. So we're looking at the GDP of Mozambique and the surrounding area on the left and the Houston area on the right. And you can see these light colors are higher GDP. So Houston has a much higher GDP than Mozambique and the surrounding area. And what this tells us is not only how well a location can prepare for a natural disaster like this, but also what capacity they have to respond after a natural disaster has happened. So this can tell us how much aid we might need to send into a location and how well a place might be able to recover from that disaster. Another interesting factor to look at is the impervious surface. So you notice that Hurricane Harvey caused significantly more infrastructural damage than Cyclone Idai did. And now we're zoomed into the Beira area of Mozambique on the left, which is the main area where Cyclone Idai made landfall. And you can see Houston has way more impervious surface than the Bay Area does, which is kind of a proxy for how much infrastructure there is there. And this is a big part of why Houston has so much more infrastructural damage than Cyclone Idai did. If we want to think about why those fatalities were so different, Cyclone Idai had so many more fatalities than Hurricane Harvey. One interesting way to look at that is your accessibility to move around within a place. So we're looking at right here on the map, accessibility to cities. And you can see that these dark red areas take a very long time to move around and get into a city if you're trying to evacuate. So around the Bay Area, there are a lot of really secluded areas that are hard to get out of. In Houston, everything is this really light color, meaning that it doesn't take you very long to move around and try to get out of a place if you need to. And you can also see Houston has much more connected roadways and it has many more airports if you're trying to evacuate when a storm is coming or send aid after a storm has happened. And the last thing that I want to look at in terms of how many fatalities you might have in a storm is how well you can communicate that a storm is coming. You'll see that Mozambique has a much lower access rate to the internet than the United States does. So this tells us that the United States would be much more able to tell citizens that a storm is coming and keep them updated with the latest news and events and help them prepare for that storm or tell them to evacuate in a much more timely manner. So I've just shown you a few examples of how you could use Resource Watch to look at contextual data from previous disasters to get a better understanding of what factors contributed to fatalities or infrastructure loss or other areas that you're interested in. We could also use some of our near real-time data sets on Resource Watch to track current disasters while they're happening. And we also have some really great predictive data to predict which areas might be at the highest risk for experiencing a natural disaster. So first, let's look at how you can track near real time what disasters are currently happening. So just last November in Northern California, we had the really disastrous Camp Fire. It was very deadly, and we tracked that in near real time by showing the satellite imagery, showing these smoke plumes moving around, and also our large fires data set, so you could see exactly how this fire was spreading. So this is our first example of a recent natural disaster that we tracked in near real time. We also had a number of large fires that occurred in Mexico in May. These fires created huge smoke plumes, which caused a lot of air pollution, and Mexico City was actually declared to be in a state of emergency during this time. So here you're seeing a screenshot of the large fires that were happening in Mexico, as well as the smoke plumes that went along with them. So you could use something like this to track which communities were not only in danger of fire, but also in danger of having really high levels of air pollution during that time. If you're more interested in predictive data, one of the data sets you might be interested in is our sea level rise data set. So this shows you which areas would be inundated with water at different levels of sea level rise. So you're seeing here New Orleans has a really huge impact from the sea level rise, and you could overlay this data set with some infrastructure data sets to see exactly what infrastructure might be affected in these different scenarios. We also have a great landslide susceptibility data set, and this is shown at 1 kilometer resolution. So if you're expecting something like heavy rainfall, you could zoom right into the area that you live in and see if you're in an area that might be more susceptible to landslides. And then the last data set I'll show you is our fire risk data set. This is one of our near real-time data sets, and it uses weather data like temperature, humidity, and wind speed to see which areas are at the highest risk for having the start and spread of a vegetation fire. So this is updated every day, and it gives you a really great idea of what the current risk is in different areas. The last thing I want to show you is our metadata. So all of our data sets that we have on Resource Watch have a really great metadata page that you can find through the Layer Info and the More Info button. And we give a sort of a plain language overview that tells you what the data set is, why it's important. We talk about the methodology. We tell you exactly what you're looking at on the Resource Watch map. We also warn you about any cautions you want to take when you're using this data. And we also have some useful information like the resolution or how frequently it's updated. And we're currently in the process of changing all of our data sets metadata to this format as part of our commitment to being the best possible access point to data so that you can really get a strong understanding of exactly what you're looking at. To make things even more useful to you, we offer the option of sharing data that you use for your research regularly or that you have found really useful. You can use this link to tell us what data sets you love. If you suggest something to us, we can often get it on the site within 10 days if there's some sort of urgency to put it up. And also, if you see a data gap that you wish we had data for, you can let us know that too, and we'll go out and search for data to try and fill that gap. So I wanted to make sure you had the points of contact of all the Resource Watch members who helped put this presentation together. You can reach out to us if you have any questions or anything to suggest to us. I would also encourage all of you to go to our website and sign up for a newsletter. It gives you new data sets every month. It has our latest blogs, and it gives you tips for using the platform. And I'll also put up the context of the Aqueduct folks who helped out today. And please do feel free to reach out. We really want these tools to be useful to you. We want to know how you're using them. And we would also love to gain feedback on how you think they could be more useful for us. So with that, I think we'll take any questions.
Thank you, Corey, Samantha, and Amelia. We encourage all participants to go to the websites provided by the World Resources Institute and the New York State Department of Health to explore the suite of tools and data platforms that they provide. We will now proceed to the question and answer session, so please type your questions in the question box, and we will respond to them in the order that they are submitted. Okay, so for question 1, could it be possible that the match between observations and the model in Florida is better than in New York is caused by the elevation? The monitoring stations are at a certain elevation, while the 1 kilometer MODIS data is the average over the whole area. So Tapasum, I think this might be a question for you.
All right, so the question is that would elevation be a predictor of, how the correlation between the monitor data and the MODIS data differs between Florida and New York State? So that's an excellent suggestion. And right now we are in the process of looking and comparing our correlation results between New York and Florida. So, and this should be coming out. I do not have results to share as of now, but please stay tuned for upcoming publications from our team. And that is one consideration that we are keeping in mind. So thank you. And along with, closeness to water bodies. So that's one, and the difference in geography between New York and Florida. Florida has more coastal areas and obviously has a hotter climate. So we are trying to keep all of those into account when we compare estimates. I hope that answers your question.
Great, thank you, Tabasum. Question 2, if you lower the watch/warning thresholds, do you change the risk? Or do you increase the time to take action to avoid the heat and therefore the risk? Risk is still a function of temperature. Policy should provide for better outcomes.
Yep, thanks for that question. You are correct. We do not really modify the association between temperature and health outcome. Our research suggests that when a person is exposed to temperatures higher than 95 Fahrenheit, they are at a significant risk of heat-related illness. So through a lower warning criteria, our aim is to increase the awareness of this risk for illness. And so individuals can modify their behaviors to reduce exposure to these extreme temperatures, such as maybe not going out during the hottest part of the day, or to ensure that they have access to air conditioning. On those days, employers and athletic directors, are given these warnings as well, and they can make sure that all outdoor workers and athletes stay hydrated and take precautions. So that's our aim with the lowering of the warning criteria. And since we work with the National Weather Service, this is, these warnings are given out throughout the region, and they are given out through the television stations, radio stations, the phone apps, social media campaigns, what have you. So.
Okay, question 3. Is the link to the story map from Tapasum's presentation already public, or will this link later be communicated to the participants of the webinar?
The story map is under development. That's why I had the draft sign there. So we have a review process. We do work with our outreach and education department. So we're still under, developing those messaging, and it'll look more polished, hopefully, when it is published. But it should be available at our website, and I can put the link to our website in this when we put up the answers. And then, when it is available, it will be available through our website. So you can see that there.
Wonderful. Yeah, as soon as we get that, we'll be sure to post it on the ARSET website. And so question 4, regarding climate change and health in New York, is the tool interactive, and in what environment was the tool built? Also, what program/software did you use? I'm interested to apply a similar approach to local municipalities or departments.
I am assuming that this is referring to the story map. So that is interactive. It has many interactive features. You can, click on different jurisdictions. You can look at specific documents related to, like, our county heat and oil profiles. You can link out and see the profile for that county. You can compare different years, climate trends during different years. So there are interactive features in there. There are videos that will be put up along with it. And we're linking out to the National Weather Service site and our other programs like the Climate Smart Communities program. So there's a bunch of resources within that story map that people can choose. It was developed under, or it is being developed using ArcGIS Online, and so I would, it is a neat tool that has been provided by ArcGIS Online. It is fairly easy to pick up. So if you are, comfortable with doing spatial analysis and have some maps that you want to put up, an ArcGIS Online account will allow you to take your shape files and put them up in a story map format. So again, I can put in my email. So if you're interested in developing it for your own jurisdiction, we would be happy to share, our techniques and what we've done with you. And if you're in New York State, we'd be happy to assist you with data that we have.
Okay, question 5 looks like another question for Tabassum. In the example in New York, did you find significant differences according to poverty levels? Is population below poverty more vulnerable in New York? How did you decide on the socioeconomic variables? Could you please add more information about the data set that you used?
So the details of the vulnerability analysis are again available through our website, and I can send a specific link to the vulnerability index. These were identified from a comprehensive literature review. We use census data, and as expected, areas with high proportions of individuals living below the poverty line level are at a high risk. So yes, socioeconomic factors were definitely considered.
Okay, question 6. How is the public being alerted about daily heat warnings? For example, is it an app, or is it text message, or is it through the media?
So since we partnered through the National Weather Service, it's neat. We feed into all of their systems, so they do have apps. They send out text alerts when there are extreme weather events. And also, you can see those National Weather Service warnings pop up when you have a thunderstorm or, rain, and the same mechanism is used for heat warnings. So these are transmitted to local TV stations, radios, channels, and then the National Weather Service and the New York State Department of Health have their own social media handles, Facebook and Twitter, and so they go out through those as well.
Great, thank you, Tabassum. And would you please ask Tabassum if they are also coordinating with urban planning departments or colleges? Planners often are responsible for long-term coordination of seemingly disparate resources and like visual data. As planners have to incorporate more climate change analysis into local plans, these tools could be very valuable.
Yes, thank you. Our collaboration with the Climate Smart Communities program is neat in that manner because we, as a health department, we don't really have a direct connection with the urban planners, but the Climate Smart Communities program actually has different organizations come together for specific local jurisdictions, and urban planners are a part of those mechanisms in most cases, and this helps us connect with this audience and to make them aware that about the public health benefits of including climate resilience in urban planning. So future benefits. We've also done some cost analysis about the burden of illness that would be prevented and dollar amount saved, which is always helpful when you're trying to plan. So yeah, so that's our way of connecting with these audiences, is our Climate Smart Communities program.
Question 8. What's the source of inundation data? From satellite data analysis or from historical in situ measurements, or both?
Great. Hi, everyone. This is Sam from WRI. Can you hear me okay?
Yes, we can, Sam. Thank you.
Okay, great. Thanks so much for the question. So we simulate flood risk using a cascade of hydrologic models within this modeling framework called GLOFRIS. So that's the Global Flood Risk with Image Scenarios. And within this modeling framework, we apply different data sets and models. So for our riverine floods, we apply a hydrologic model called PCR GLOB. For the coastal data sets, we use something called the Global Tide and Surge Reanalysis data set. I can repeat that if you need it. And these are produced by some of our data partners in the Netherlands. A good starting resource for this is a paper called A Framework for Global River Flood Risk Assessments.
Okay, great. For question 9, in which countries is Aqueduct available?
Yeah, so Aqueduct should be accessible in all countries, and our data is global, so you should be able to find data wherever you're looking.
Great, thanks, Sam. Question 10. Houston had more infrastructure damage simply because it had more infrastructure. The question to ask is, given an area of urban development, how much damage occurred? A measure of proportion damage over just the urban areas, ignoring non-urban areas, may be more insightful.
This is Amelia from Resource Watch speaking now. And yeah, I put that slide up just to sort of give you an idea of the types of relevant data that we have on Resource Watch. It wasn't any sort of formal analysis. But if you are interested in digging deeper into these questions, our API actually lets you do some basic analysis on it. So if you had a geography that you were interested in, you would be able to upload that geography, and you could do the sum of the impervious surface over that area, or the average. So you can do some basic raster statistics like that on our API. And also all of our data sets, once you go to the metadata page, have either a direct download or a download from source link, which takes you to the source page, and you can download that raster or whatever type of file it is for yourself if you want to do these more in-depth analyses. So I would encourage you to, if you're interested in that data, do any sort of analysis that you like, either through our API or by downloading the data set yourself.
Okay, thank you, Amelia. So question 11 has to do with ingesting software to be used from WRI. So what is the most suitable mapping software that should be used for WRI tools introduced in the presentation?
This is Amelia again. I can answer that. So all of our tools are actually available just to use directly online. So you can use it through any browser and get some sort of idea of what the data look like and do some exploration. You can visualize them there. or click around and see specific values. If you want to do more in-depth analysis, we also have download links for all the data on ResourceWatch and Aqueduct, and you typically get either a shapefile or a raster. Occasionally on ResourceWatch, some of the data sets might be NetCDFs, but you can use any sort of spatial software that you are comfortable with. You could use Esri products or QGIS or Python. So yeah, they're just in typical shapefile, raster, traditional formats. So whatever you feel comfortable using if you want to do more in-depth analysis.
All right, question 12 looks like it might be for both WRI folks and Tabassum. So can we use data sets for our research, including the screenshots of the data representation for the presentations, by mentioning the source and or website?
This is Amelia. I'll speak first since I've got our mic unmuted already. For ResourceWatch, you are welcome to use any screenshots. We're also going to be adding an export PDF feature soon, and I showed you that export for embeds. And we would welcome you to use any of that. And we have on our metadata page the citation that cites the original source data, and it says access through ResourceWatch if you're using any of our visualizations. So you're welcome to do that for ResourceWatch. And I don't know if Sam wants to answer for Aqueduct.
Yeah, for the Aqueduct data, we have released all of our data along with a technical note, and that technical note is what you can cite if you're using our data.
Hey, this is Tabassum from New York State Department of Health. So yes, you are welcome to use our slides with proper citations. Also, if you, so the data is not available yet, but when it is, and if you would like to, before it is made publicly available, since the platform is still being developed, if you would like to get the data sets, please feel free to contact me. We also are developing an executable where you would be able to get these data sets directly from NASA's website, and also use the downscaling algorithm to downscale for your jurisdictions, across the contiguous United States. So yes, please feel free to contact me, and I can connect you with these resources.
Okay, thank you, everybody. Question 13, what is the correct form to cite the outputs from Aqueduct and ResourceWatch?
For ResourceWatch, we recommend that you cite the original data source and then followed by access through ResourceWatch. And we actually have those citations right on our metadata page. So if you're looking at a data set, just go to the full metadata page and you'll see it right there, and you can copy and paste that.
Wonderful, thanks so much. Question 14, what type of data is available for cities with reference to fire risk?
So on ResourceWatch, we have tons of data related to fire. A few of the ones I showed you, that fire risk data set, or it was the fire weather data set that was in the demo. We also have data showing current fires and large fires. Maybe you would want to look at some things like the standardized precipitation index to see how dry an area is. We have a data set on vulnerability to floods and droughts. We also have some of the aqueduct data that are related to droughts, which may make things more likely to have a fire. So I would encourage you to just go into our catalog and type in fire risk and see what pops up. We have tons of data, and we're adding new data every week.
Wonderful. Question 15, are the data in Aqueduct in raster format? How can we extract the data from the tool?
Yeah, great question. So on our tool, we have a toolbar at the very top. One of the drop-downs says data. If you just click on that data tab, and the very first entry you see will be for our data download. And we provide the data in a few different formats. Everything is contained within one master database. The shapes that we use to create that database are our subbasins, so our watersheds. And then we also have political boundaries, so countries and provinces, as well as aquifer shapes within there. And that's available as either a CSV or a shapefile.
Okay, question 16. I would like to ask about Tabassum Insaf's presentation, specifically on slide 17. Is there any correlation between heat stress and acute kidney failure? How much does one correlate them?
Yes. We did look at a couple of different health outcomes, and thank you for that question. I kind of skipped over my results for acute kidney failure in interest of time, but we do find that there are significant effects, and the most prominent effect occurs at 1 day after an extreme event. The results of our health analysis have been published, and so I can put in a link to our research paper, which I do the results. But specifically, we did find that the risk of kidney failure increases even up to 7 days after a heat event. I'm hoping that answers the question, but I'll put in the links to the paper.
Thanks, Tabassum. Question 17. There's plenty of global data sets available on the website. What's the adoption rate from national government agencies in using such great data sets and tools? Is capacity building a felt need for these national agencies to adopt these technologies?
Hi, this is Amelia from Resource Watch, and I'll just speak briefly about Resource Watch. But yeah, so governments are one of our target audiences, so we would highly encourage any members of the government to use our data. We're currently trying to reach out to people using Resource Watch and collect some of their stories and learn more about how they are using it, since we launched just about a year ago. But if you know of any members of government that might be interested in this type of data, we would love for them to reach out to us, and we provide support to anyone who's interested in learning more about how to use Resource Watch, and we'll work with them to try and understand the website better, or help them through any problems they may have.
Great, thank you, Amelia. Question 18. If I need to publish my work in a research paper, how can we use the data from the given tools?
This is Amelia again. If you would like to download data from Resource Watch, as I've mentioned, we have that direct download link. If I'm understanding correctly, you're asking how you can access the data. So we have download links, so you can directly download those rasters or shapefiles or whatever they are and do any sort of analysis related to your research that you want.
Hey, this is Tabassum. So please feel free to contact me, and we can talk about how you can access the data since it's not available yet, but it should be publicly available soon as well.
Question 19. I'm interested in the computational infrastructure required to store these tools and databases. What are the hardware requirements for WRI's Resource Watch tools?
So in order to use Resource Watch, all you need is an internet connection and some sort of browser. It's just a website that you go to, and you can directly look at any of the data sets that we have and interact with them there. If you do want to do any more in-depth analysis and download it yourself, you would need a computer that could run whatever your spatial software is that you have, your Esri or Python or whichever program you like. So it kind of varies depending on what tools you're using. But if you want to access Resource Watch and see the data and interact with it there, all you need is a browser and an internet connection.
And hi, this is Emily Nilsson. I'm also on the Resource Watch team with Amelia. And if the person who asked the question was more interested in the backend infrastructure for how we store those data sets, we have them all stored on an API like Amelia mentioned, and we use a microservice architecture for that API, and it's run on Google Kubernetes engine. So we've got this whole API that stores the data, that stores the configuration for how the layer is rendered on the map, that stores the metadata, and all of the information associated with each of those data sets, as well as a number of other things that our data platforms rely on. So if you have any questions about how that API infrastructure works, then just email us on the Resource Watch team, and we would be happy to provide more information on that.
And it sounds like a follow-up to the last question is clarifying that last question. I'm interested in your institution's infrastructure.
So this is Emily again. So to that person, is what I was talking about with the infrastructure of the API answering that? I'm not sure I completely understand what institution's infrastructure means.
And question 21, if the Indian government wants to collaborate with Research Watch, what is the proper way to officially approach WRI?
With Resource Watch, we're a pretty small team and we work really closely together. So you can email anyone reach out to anyone who was on those slides, get our contact, and just let us know, that you want to work with us and maybe give us an idea of what sort of work you're interested in doing. And we will, whoever you send your email to, we will make sure that you get to the most relevant person and try to get you connected. So feel free to email any of us.
Thanks. Question 22 is a question for Tabassum. I'm interested in the processing of downscaling coarser resolution data from climate models using higher resolution local climatological variables. This is similar to the extreme heat in New York example. Can you give a summary of the process, the steps in data collection, manipulation, processing, verification, and what the recommended software is to use?
Okay, so this is sort of a little bit outside my area of expertise. I'm the epidemiologist here, but I will connect you to our team at the University Space Research Association, who is responsible for the downscaling. We will actually, our paper for the downscaling methodology has just been, it's in the second round of the review and should be published soon. So we will. I'll put that link in the documentation as well when it becomes available. But I can, if you email me, I can put you in touch with our scientists at the University Space Research Association who led the downscaling algorithm.
Question 23. May I use WRI resources and data sets to develop teaching materials and laboratory exercises at my institution? If so, what sort of acknowledgement is needed?
Hi, this is Amelia. At least for Resource Watch, we would encourage you to use these, our materials in your teaching and laboratory exercises. I would say just mention that you're using Resource Watch and maybe, say that in any handouts you have. But if you're interested in developing more classroom materials for Resource Watch, I would love to connect you with Corey. I think her email is on the slide because she's currently working with some teachers, trying to get them to incorporate Resource Watch more. So feel free to reach out and I can connect you with Corey if you want to talk more about that specifically for Resource Watch.
Yeah, and for Aqueduct, we're thrilled to have our materials included in lesson plans, and you can visit our website and see our FAQ for just some details how to do that.
Okay, question 24. For determining socioeconomic risk, which indicators have been considered?
Again, so the socioeconomic risk is part of our vulnerability analysis, and I have put in a link to the manuscript that lists all the variables that were used for the analysis. We did a principal components analysis for that portion, and the socioeconomic data included education levels, unemployment rate, and number of people below the poverty level. And again, I'll put in the link to the paper as well, so you can look at all the details.
Well, it doesn't look like we have any more questions, so I want to thank again our colleagues from the World Resources Institute, Corey Filio, Samantha Kuzma, Emily Nielsen, and Amelia Snyder, as well as our colleague from the New York State Department of Public Health, Tabassum Insof. It was great to hear your presentations today and hear about all the great work and the tools that you're providing, open source tools for people to use. And again, we encourage everybody to go to your websites and explore more so they can see how they can be used in their own research and also application. I want to remind everybody on Thursday, we will conclude the training on Earth observations for disaster risk assessment and resilience by inviting colleagues from the Pacific Disaster Center to present on what data, applications, and strategies they use for disaster risk reduction, response, and relief operations. Also a reminder to participants, both homework assignments must be submitted online by August 30th to receive a certificate for this training. The homework can be found on the ARSET webpage for this training. I would also like to acknowledge, outside of the presenters, my colleagues here at ARSET. That's Amita Mekta, Selwyn Hudson-Odoi, Brock Blevins, and Elizabeth Hook for their contributions to this training. And thank you all, and we hope to see you on Thursday for the conclusion of this training.